Welcome to the second video in our series, Getting Started with Model-Driven Engineering. In this video, we're going to provide an example of using a model-driven engineering approach, and to do that, we're going to demonstrate it using Epsilon, one of the many model-driven engineering tools that are available. In our first video, we discussed broadly the idea of what model-driven engineering is, and that is that we have some ideas or knowledge that we then encapsulate or describe using models, and from those models we produce artifacts or an end product. However, what we never discussed was what we mean by the word model in the context of model-driven engineering. So before we go any further, let's put some definitions to what we mean by model. Firstly, models in MDE are abstract representations. This can be of a physical thing or some concept, and that abstractions can have more or less detail than the things that they're representing. For example, a toy car is not a copy of a car. It is abstract in some way, which is to say that it is not an identical copy. There is something about it which is different. Now, typically with a toy car, the scale will be different. The size of the car being different means that it is abstract in some way. The materials and features between cars and toy cars can be different. Again, another example of how they are abstract in some way. The next point that we need to consider is that our models are representations that we create for a specific purpose, and that certain models are created with a particular purpose in mind, and such wouldn't be useful or may not work for other purposes. For example, we could make a cardboard model of something physical that we intend to create. This will be suitable for measuring and handling. However, it would not necessarily be suitable for testing a load-bearing capacity, particularly if the end product was actually going to be made from concrete, a very different material with very different properties. And thus, the representation of the thing that we intended to make with cardboard is only suitable for certain tests. The next thing to consider, with MDE, we seek to create models to represent things. However, the models that we're producing are not the end product in themselves. They're simply a tool that we are making to help us create a final product that we need to deliver. We use models because they are cheap, they can be tested, they can be transformed or modified, and that they can be reused. However, when we undertake a model-driven engineering project, the deliverable thing that we are seeking to provide is a product. It is not the models themselves. So what is model-driven engineering? Is it a practice or is it a set of tools? I like to think of it as both. As a practice, we take modelling and the modelling languages as central assets in our projects. These are going to be the representations of the product that we want to produce. The modelling tools are the things that we're going to use to create the languages and the models, and then automated tasks that we will perform on our model to fabricate our final product. Ideally, our model should also enable us to get other valuable things that will support our product. For example, we may do some validations of our model to prove that our end product conforms to some standards. It is also possible that we may extract some information from our models such that we can create documentation. And ultimately, if we're dealing with a software project, our model should deliver some code. And that code could then be integrated with other components to build the final product. There are several common misunderstandings about model-driven engineering. One of them is that you have to produce the entire product using model-driven engineering. This is not the case. It is perfectly acceptable to use model-driven engineering to simply deliver a small software component for a much larger system. Another one is that a single language or model can represent everything about your product, such that you can fabricate the product from that single model. This is often not the case. You may need one or more languages and one or more models to encapsulate all the different aspects of your product, such that you can then produce from a combination of these models the final asset itself. Finally, you might hear comments such as models are only good for design or generation of code. This is not true. Models can be used for many different things throughout the project lifecycle. One of those things is to actually transfer knowledge from one team to another. To give an example of model-driven engineering, I've motivated the following background story. Part of a larger software development team, we've been asked to produce a state machine. It must be perfect in every way, tested, and meet some rigorous requirements. The state machine is shown on the right. The three ovals represent the states, and the arrows represent the valid ways in which those states can be changed. The system will only go through those three states in the direction of the arrows indicated. The goal is to deliver a perfect Java class implementation of this state machine, without writing the Java code by hand. To do this, we're going to have to create a modeling language that lets us express the model that we can see in the right, and then that model will then be transformed to implement the Java state machine. In reality, this is an awful lot of work for creating a single Java class. The appropriate use of model-driven engineering is something best discussed at the end of the video. For now, this simply serves as a motivation to demonstrate the practices of MDE such that we can gain some understanding. So you may still have some fear. You're not understanding what is going to be required of you, and you're not quite sure whether or not this is the right thing to do. So let's try and manage that fear a little bit more, and then it will help us eat the frog and find the rewards of model-driven engineering. For our simple state machine example, we're going to sit and write 5 text files. The first one is going to be to create our modeling language. The next will then be to use that language to create the model itself. And then we're going to write 3 small programs which will perform different tasks: validation, generation of Java, and then a graph viz diagram. Each of these programs are going to need to be run against the model, and we can think of this as simply being like running a compiler against code or scripts on some files. In a real world, at scale, on a large software project, model-driven engineering is going to be more complicated in the sense that we will have to deal with collaborations, meetings, sign-offs. So let's enjoy the simplicity of this classroom scale, in which case we just need to write 5 text files and run those programs against the model. Epsilon is a free, well-documented model management toolset. Picking an MDE toolset in itself can be an overwhelming challenge, and that's not what we're here to address today. Inside of our Epsilon toolset, we will find the following tools and notations for handling modeling languages. Firstly, there's emphatic, which is used to define the modeling language itself. Then we need to create a model using that language. To do that, we use the flexmi notation. To perform tasks with our models, we use the programming languages provided by Epsilon. These are all derived from EOL, the core language. Depending on the task, we will use a particular programming language, such as EVL for validation of models, and EGL for generating things from models. There's a lot more to Epsilon than this, and there's a lot more modeling tools than Epsilon. However, this is sufficient for what we need to demonstrate today. Getting started with Epsilon is made incredibly easy thanks to the Epsilon Playground. We don't need to download or install any development tools. Using a browser, we can go to the Epsilon Playground and we can see the various text files that need to be created to enable us to produce models and products from models using the Epsilon tools. The Epsilon website contains the documentation for each of the notations that are required. These can be accessed using the little question mark icon. Playground is a bit more than just an editor. You can actually execute the programs that you're developing against a model within the confines of the Playground. Let's have a look at the Epsilon Playground website first. I have opened the Epsilon Playground and adjusted the layout of the screen such that we can see the meta model, which is our modeling language, which is defined using emphatic, and the model, which has been defined using FlexMI, more clearly. You'll notice that I've generated graphical representations of both the modeling language and the model itself. This makes it easy for us to understand what each of the notations are trying to express. You'll notice that the meta model, or the modeling language, expressed using emphatic, has an object-oriented programming style. We use classes and attributes to define the concepts that we need for expressing our models, and that FlexMI, whilst it has an XML style of notation, and within the tags of our XML notation here, we can see the various concepts that are expressed in the meta model language. Thus, we have a machine which has states and various transitions. Is the validate state machine example. As such, there is also an EVL program, which runs two rules against the model, and if we click the play button, we can validate the model and see which of these rules have been violated. Playground expresses the problems with our model using a graphical notation. If we zoom in a little bit, we can see some of the violations that have occurred. There is a duplication of transitions, and one of the states has been incorrectly named. We can go back to the model and we can correct the problem with the state, and we can remove the duplicate transition, and then perform a revalidation of our model. Now we can see a visualization of the model without any errors indicated. The Epsilon Playground is a good introduction to the Epsilon toolset. However, it has some limitations. It's not possible to save these projects or to version control them. For that, we need a full IDE environment. We need to move towards the Eclipse IDE such that we can work on a much larger scale with our modeling projects. Depending on the types of tasks that we're performing, we will need to run one or more Epsilon programs against our models. Going back to our example project with the state machine, we wanted to perform a validation, code generation, and a visualization. We can take our Playground examples and download them. Several flavors are available, but the one that we're interested in is Ant Eclipse. Having downloaded our example, we can expand the file Each of the downloads from the Playground include a metamodel.emf, which is your modeling language, a model.flexmi, which is the model, and a program dot either EGL or EVL, which is the program that you've been developing in there. In addition to these, you'll find the readme.md file, which will give you instructions on how to obtain the Eclipse Epsilon environment, and then how to execute your build.xml file, which is an ant build file. I will now demonstrate the process of doing this. Unpack the Eclipse installer. If you do not have a JRE or JDK installed, you will need to install one either through your Linux distribution package manager or download one from the internet if you're using Windows. The Eclipse installer can be used to install many different products. We are looking for Epsilon. Click Install, and it will simply use the available Java installation and turn out the installation into the folder indicated. We can now click Launch. The installer that we've used provides the Eclipse IDE with all the necessary components for developing Epsilon projects. We go to File and Import. Projects from a folder or archive. Find the directory that we downloaded and expanded the playground example into, and click Finish. And we have imported all of the playground files. We can see our modeling language, the metamodel.emf. The IDE provides syntax highlighting. We can open the model, which is a flex.mi file. We can see the EVL program for validating the model. The additional files that are included are the README and this build.xml. Ant build is a script that is written in an XML format, and it is included within the Eclipse IDE environment. Ant is available to run and perform the various modeling tasks that you want without needing to install anything extra. If we right click on the build.xml file, go to Run As, Ant Build, we need to set the runtime environment to be the JRE, the workspace, as noted in the documentation. This will enable Ant to execute the program provided against our model and have all the dependencies met. When we click Run, we can see that Ant has executed program.evl against the model, which has returned no errors. If we go to the model, we can insert an error, save the changes, and rerun our program using the Ant build. And we can see this time that the validation has failed. It will be possible at this stage to download multiple projects from the playground and combine them within this one development environment space, and adapt the Ant build XML such that we can execute multiple programs against a model, which would enable us to perform both validation, code generation, and the generation of a graphical representation of our model. Let's download those projects and see how these can be combined. We need to rename each of our programs such that when we copy them into the folder, they're not going to overwrite one another. This program generates the GraphViz. This program generates the Java class. Let's rename our validation program. Going back into the Eclipse IDE, we can refresh the project space, and we can now see our additional programs. Let's look at the build XML script. The build XML script has been clearly commented. As such, we can see that there are 4 phases. One where the model is loaded, and then the following step, program EVL is being executed against the model that has been loaded into M. Then we dispose of the model and we refresh the playground example. This is the equivalent of highlighting our project and clicking refresh. This will update Project Explorer and show any new additional files. If I try to run this build XML, we will get an error because I have renamed program.evl. The errors that we can see being expressed by Ant here are because it cannot find the program.evl. Let's rename that. Whilst it has failed, we can see that the program has actually executed and managed to find our program. Going back to our example project with the state machine, we wanted to perform a validation, code generation, and a visualization. To do this, we need to modify an Ant build XML file such that we can run multiple programs. With our other playground examples, they have their own build XML files, and in them we can see that the program execution statements are different for the one that's required for the EVL. To have Ant perform these various programs one after another, we need to copy these sections of the files into a single build XML. Let's do that. We also need to update the program name. This one is going to generate our program into a text file called generated.txt. Again, we'll notice the same statement has been made for for generating the graph viz. So we can simply reuse the same statement in our build XML. However, we're going to need to change the target file. Let's do that. Now we have a build XML script which will have and perform 3 tasks. It will first validate our model using the validation program. It will produce a Java implementation using the java_program.egl, which is going to output to Java_generated text. And similarly, the graph is going to be produced by another program, which will then output to the graph_generated.text. Let's execute this build. Because the validation has failed and stopped at the validate program stage, we need to correct the problems with our model. And then we can rerun build XML. This time, Ant has managed to do a successful validation, and so it's proceeded to the next task, which is to then generate the Java, and as that was successful, it then generated the graph. We can see 2 new text files have been added. If we rename our generated Java, the Java notation should be correctly indicated by Eclipse with syntax highlighting. The pattern of the build XML file provided by the playground is well commented, such that you can see the load stage that will load a model, the run stage which will execute your various Epsilon programs, and finally the exit stages where the model is cleared and the environment is refreshed such that you will see new files. Alternatively, instead of compiling all of the tasks into a single build XML, you could carefully rename each build.xml file and have each stage as a separate executable for an Ant runner. However, the fact that if a validation stage can fail, block the run of a generation, it may be more advantageous in some cases to combine certain programs together such that if any program fails, the process of building your model into a product is stopped at the failing stage. So in conclusion, we can start by designing a small language and model within the playground and potentially expand that to include some sort of a program for a process. We can download and export those files into a local Eclipse IDE space, which we can now use Git version control and manage the changes to our models, languages and programs. We can combine multiple programs into a single build XML, which will enable validations to block the executions of generations if those tasks are ordered correctly. Having seen the process, we can now understand that an MDE approach would be suitable where a single description can be used to produce more than one output. For example, our code has been generated along with a visualization of our state machine. We're getting 2 outputs for the effort of one description. This is a good use case for MDE. However, our example has only touched the surface of what can be done, and our little state machine example actually has great potential. MDE tools are not standalone, and they can be combined. We can use common model notations to move from one MDE tool to another. For example, a hidden reward for our efforts of modelling our state machine lie within our generation process. At the moment, we have designed a modelling language for expressing a state machine, as to which we could express different state machines using the same modelling language, and we could produce Java implementations of each one. If we wanted to add C# as an output state machine format, we would need to write another EGL program. And yes, we could have two EGL programs and produce a Java and a C# implementation of any state machine. But what if we wanted to produce it for more languages? This would require us to write multiple EGL programs. However, we could combine our approach with a different tool. If we wrote an EGL program that could output a state machine compiler compatible model, although technically this is a compiler and not directly an MDE tool, it would be possible for us to then take one description of a state machine and implement across several languages the same state machine. This is where model management and model transformation techniques can be extremely productive. And thus, our little pipeline example here goes from being able to express a state machine that is generated in Java to being able to express different state machines and then turn out implementations in multiple languages at the same time. And thus, a hidden reward is revealed. Model-driven engineering is best applied when, from a single description, you would like to obtain multiple outputs. And this is a hidden reward of the effort for doing the model-driven engineering process.